All right, guys, so we've just entered the distributed load section, and just letting you know right now, from here on out, this class is going to get crazy as hell. But it's okay because you're too far deep to quit now, so it is what it is. Just keep pulling through, right? This problem, there's two solutions. There's one on Chegg, and there's one from the author. None of them are right. Uh, the book solution, I don't know what happened towards the end, but he just like rounded for some reason. That was incorrect. And then Chegg, they got their stiffness matrix wrong, just FYI. But on this problem, I'll show you how to do it, and I'll even show some screenshots of ChatGPT at the end to kind of just prove that this solution is correct as opposed to the book solutions online. So same thing, right? The only difference, I mean, there's no difference, right? I'm not comparing it to anything, but this really is just a typical problem, except the only modification was that double bending right at the center that you're seeing. Okay, so if it was just one continuous same stiffness beam, this would have been a very basic problem, and it would have made more sense intuitively. But because of that, I don't even know why it's the first problem. It's not like it's a problem on crack. But you know what, let's go ahead and get started. The video is already long enough as it is. I try to keep things short, but I really don't want any comments saying, hey, how'd you do this and that. I like to go things in detail, and I promise you after this video, you will not have a question, at least on this specific problem, right? So let's go ahead and get started. All right, so same thing as all the other problems, right? We start off with the stiffness. In this case, we're dealing with three beams, right? It's this beam right here, that beam, and that beam. This one has twice the stiffness as the other ones, not to scale, right? And also the printer at work wasn't working, so I had to write it down. They give you the distances, right? L over 3, L over 3, L over 3. So it's just length across your entire length, right? So it's W times L. That's the load that's being applied. So because we could just see that it's symmetrical, that's usually the first approach, right? If you wanted to do the whole system, you're looking at 1, 2, 3, 4, 5 nodes. You do 5 because you have to analyze right down the middle, because there's going to be, boundary conditions right at the middle. And it helps your problem, but you're talking 10 by 10 matrices at that point, right? 5 nodes, 2 boundary conditions for each. So it gets crazy. So you want to do symmetry first, okay? So cut it right down the middle, exactly down the middle. You have an L over 3 beam, which is that one. And then you have an L over 6, okay? You have nodes 1, 2, and 3, so that helps us. And there's a roller here that we add. It's a fixed wall and then the roller, so there's going to be some displacement. But we know phi is 0. Now, you might think, yeah, phi is going to be something, right? Because, I mean, that kind of looks like a cantilevered beam, but it's fixed, remember? So just look at the whole beam to help you, like, think about it in better detail. If you apply a force right down the middle, it's all equal, right? So if you imagine you just have one force going down the middle, you're going to have a displacement curve that looks like this, like a U shape, right? Well, right in the center, you have 0 slope. So that's your boundary condition, okay? So phi 3 is going to be 0. I'm going to go ahead and just show you the boundary conditions. Another thing to mention, to make our problem easier, to not have to deal with fractions, for now, we're just going to do L over 3, and L over 6 becomes 2L and L, right? L is equal to L over 6. That's going to help us a lot. It's going to make the problem neater, so just keep that in mind, okay? So you start with your boundary conditions. V1, we'll start looking at the symmetric diagram. V1, phi 1 is 0, we know that. V2 is going to move some distance, so we don't know it. Phi 2 is going to create an angle, right? So we don't know it. V3, it's going to come down some distance, and phi 3, remember, U shape, so it's 0. So cool, that should be reviewed. If you don't get it, watch the previous videos and I explain it in better detail, but I imagine we're all comfortable at this step. So come down to the next step, the stiffness, okay? Forget about step 4 for a second. This beam, in this case right here, has 2 elements, right? This one and this one. So that's how we're discretizing the system. So we're going to have K1 and K2. Now, this is where it gets a little tricky. You got to make sure you catch it, okay? It's real easy to miss it, and it could fine if you didn't catch it, okay? So in this case, our first beam has length 2L. Remember, we did the substitution. So you have to put in 2L cubed, right, on your bending stiffness equation. you have to put in 2L, and then you got to cube it. So you're going to get 8L cubed. Now, that's not the only thing. You have an L inside here, okay? All that 4x4 matrix has an L. They're all over the place, right? So you got to put in 2L for every L that you see, okay? And this problem took me a while when I was doing it because I missed that step. So just FYI, I completely forgot to put the 2. So this is 12. That's going to be 2L squared. That's 4L squared times 4. That's going to be 16L squared. 12, 16L squared. That's going to be 12L, 12L, negative 12L. You get the point, right? Then that's for element 1. For element 2, L stays the same, but the stiffness increases by 2. So all you have to do is throw in that 2 inside the matrix. So this becomes 24 8L squared, 24 8L squared, negative 12L, etc. Everything gets multiplied by 2 inside that matrix. So that's K2, okay? Now hold on to that. Right now, what we're going to do is go to the nodal force system, okay? This distributed load, so the whole point of this class, right, it's FEA. You're analyzing nodes, and then you're using the laws of compatibility that the entire system deforms, and at every node it's the same deformation is what I'm trying to say, right? So in this case, this node is stuck to this beam is stuck to this beam, this element is stuck to this element between that node, and that's all FEA really is. But you can't really do that with a distributed load. So what they do for FEMAP, right, Nastran, once you start doing all that stuff, what the software does is it gets this distributed load and it just summarizes it into nodal forces, right? How can I show this distributed load as a function of forces and moments acting on my elements? And that's it. That's the whole point of this chapter. That's what you really need to understand. That's the whole goal, right? But in this case, let's continue. That's kind of what we're doing here. That's step 4, okay? So in this case, we have 2 elements, this one and this one. So I got it right here, this one and this one. I'm stuck together, but it's okay. You're gonna see what I'm gonna do. Let's stick to the first one for now. And we know by beam theory, and if you don't know it, just watch my previous video. I have a video and it has like the word proof in it. And you should be able to find it pretty quick, but it explains how that WL squared over 12 comes into these problems, okay? It also shows it in the back of the book. I think it's appendix D. And it shows you for lots of systems, right? In this case, we're dealing with a distributed load, so you'll see what case to use if you just pull up the book. In this case, we have, for the beam element itself, we have the 2, okay, so look, the distributed load is W times L. So what you do is you put WL over 2 on this side, WL over 2 on this side, and boom, when you add them together, you get WL coming down. That's why they're negative. So that explains the 2 downward forces, okay? At the beam, the beam's the element force that it's producing, it's negative WL squared over 12. That comes from beam theory. And it's clockwise, so it's negative. This one's counterclockwise, so it's positive. So these two should be the same sign, right? Because it's pointing down. And then these 2 opposite signs. Because the beam wants to do this in like within, okay? When you do C rod, C shear, all that good stuff in FEMAP, this is what the software is doing. So, I mean, if you have a distributed load, right? So in this case, the beam wants to, right? If you're applying downward force, it wants to deform that way. That's the moment being produced within, okay? And it does it for both, right? It's independent of the stiffness and all that good stuff. The nodal force system for a beam subjected to a distributed load is this, okay? So they're the same, right? WL over 2 going down, WL over 2 going down, WL over 2 going down, boom, you can see it. Both the same system. Now, they kind of change a little. Now what we have to do is incorporate that 2L for element 1. So anytime you see an L, plug in that 2L, okay? And then anytime you see, in this case, you just have L. So it just stays like that, okay? Now let's go to the next one. I don't want to show you the next step. My bad. Like that. Okay. Like that, there you go. So now you apply L and 2L, right? Just what I told you guys. So this one changes, but this one stays the same. All right, all I did was I put 2L for every L that I see here, and I just changed it. So you should be able to do that. No big deal. This one stayed the same because it's just L. But I would have done the same thing assuming it was like 3L or whatever the case would be, right? Now you see why it's better to work with these L's than L over 3. Or else this would have been real messy real quick, okay? So go to step 6 now. Now you just simplify them, right? So this is the only thing acting here, so boom, we just bring it. This is the only one acting on this node, so we just bring it. This one and this one are acting right at the center, so we combine them. This minus that will give you WL squared over 4. And since you got a positive, it's clockwise. And then these two, they're both going down, so you just add them. Negative 3 WL squared over 2. And then these two, they're just the same. All right, now these are the nodal forces acting on the system because of the distributed load. These are not the reactions, okay? So what we're gonna do is pretty much we're gonna use this to find our displacements. Once we find the displacements, you're gonna find effective forces, and then you subtract those forces to get concentrated forces. Now it's a little confusing, but you'll see what I mean in a second. Now that we got this piece, you go to the stiffness matrix for each element. So that should have been after this, but no big deal. So remember what I said, right? 2L, and then you gotta remember to put the plug in L over, what was it? 2L, I'm sorry, yeah. Since it's 2L here, you gotta plug in 2L for every L that you see, okay? So that's how you get this, right? In this case, we got 2 cubed is 8, but we want EI over L cubed for both elements. So we're gonna throw anything that's not EI over L cubed inside. In this case, it's just an 8, right? So everything's gonna get divided by 8 here. Everything's gonna get multiplied by 2 here. And then any L that was already here is gonna have a 2L instead. So if you do that math, let's do the first one, right? 12, okay. There's no L, so we're at number 12. Now divide 12 by 8, you get 1.5. 4L squared, that L was a 2L. So that becomes 4L squared times 4, that's 16L squared. Well, divided by the 8, you get 2L squared. And do the same for all of them. I trust you guys know how to do that, right? Just repeat the process and you'll get these numbers. For element 2, all you do is multiply that 2 into the stiffness matrix. So you get 24 8L squared, 24 8L squared, 24 8L squared, 24, and everything else, right? Just multiply everything you see here by 2. In this case, it's just L, so you don't have to, L stays the same everywhere. It doesn't get a multiplier. So now that you have both stiffness matrices with the same common multiple here on the outside, now you can add these matrices together. Now, this is between nodes 1 and 2, so V1, Phi1, V2, Phi2. This one's between nodes 2 and 3, so V2, Phi2, V3, Phi3, right? The only ones that get shared are V2, V2, right? V2, V2, so that 24 is going to get added to this 1.5. This 12L is going to get added to that negative 1.5. This 12L is going to get added to this negative 1.5. Then 8L squared is going to get added to 2L squared. Okay? So when you do that, you got this. Let me explain what happened here. First, let's look at the matrix. Okay? You have element 1 to 2, right? This is the 4x4 that we had here. Okay? That 4x4. Then here is between nodes 2 and 3. So V2, V2, that's your starting point, 4x4, okay? Now these 4 were the ones that I just told you that get added together. These 4 and these 4 get added here, okay? So that's how you get the stiffness matrix. Now you apply your boundary conditions. We know V1, Phi1, V2, Phi2, V3, Phi3. Plug them here. 0, 0, V2, Phi2, V3, and then 0, okay? I just created the vector. For this one, you plug in your nodal forces. So you plug these in negative WL, WL squared over 3, minus 3 WL over 2, WL squared over 4, negative WL over 2, and then WL squared over 12. Okay? Now, we're going to use these numbers to find these displacements. Okay? And I wish we had actual numbers. I hate working with variables. It's more confusing. But all I did was just plug in this as a vector, this as a vector, and then my stiffness matrix, obviously. So I'm gonna find V2, Phi2, and V3. Now that's gonna take some time because we don't have numbers. So we have to use actual algebra. But I'm gonna use this 3x3 matrix, this 3x1 vector, and then this 3x1 vector, right? Same rows, same columns. That's it. So I didn't write on the back, so I don't have to go back and forth. I wanna help you guys see this the best, right? So in this case, I just made equations, right? 3WL squared over 2. Let me make sure you guys can see. Yeah, cool. Negative 3WL squared over 2 is equal to EI over L cubed. I'm just doing this, okay? Negative 3WL over 2 is equal to the EI over L cubed. 25.5 V2. 10.5 L Phi2. Let me use another pencil. That was an ugly pencil, man. 10.5 L Phi2, right? Negative 24 V3, and boom, that's the first equation. Next one, WL squared over 4 is equal to EI over L cubed. 10.5 L V2, 10L squared Phi2, minus 12L V3. Negative WL squared over 2, EI over L cubed, minus 24 V2, minus 12L Phi2, plus 24 V3. Cool. So now that you have these three equations, you have three unknowns, three equations, right? So you just solve them. You can't use a calculator because you don't have numbers, but it's no big deal. In this case, look, just by looking at it, I made a note. V3 looks like it's the easiest to eliminate, right? You could add that to that, it goes away. And then for this one, you just got to multiply something by 2 or divide by 2. And then the trick is you use, in this case, I'm going to use the first two equations, 1 and 3, because it's the quickest one. And then I either have to use 1 and 2 or 2 and 3 or something like that, right? Point is, you got to eliminate the same variable twice. Okay, so that's what I'm going to do. Equation 1 plus equation 3, right? So I'm going to add this equation to this equation. 24V3 is going to go away, okay? And I just wrote down the equations here, but the only thing I did was I moved EI over L cubed to this side, so that became that, okay? And you do the math, okay? I'm going to go with this pretty quick, but they're correct, trust me. That became that, right? When I move that over, 25.5V2, all that stayed the same, all that. Then this one, I moved this over, and that became that, minus 24V2 minus 12L2 plus 24V3. These go away because you're adding the equations. So you're going to have two equations, two unknowns now, and you end up with this. And all this is correct. Okay, that's equation number 4. Then I'm going to go do another method, right? Now I'm going to do equation 2. So I'm going to stick to the second equation. I'm going to write that down. And then plus equation 3, but it's multiplied by half L. L over 2, right? 0.5 L. The reason I would do that is because if I multiply it by L over 2, that's going to become a positive 12L. And now I can eliminate V3. I eliminated V3 here, so I have to eliminate V3 on whatever equations I choose next. So you got to remember, okay? You got to eliminate the same variable twice. So that way, once you do that, feel free to just go through it yourself. You'll get this equation. Now you have two equations, two unknowns, right? So in this case, look, I could just add the two equations together. V2 and V2 will cancel out, negative 1.5. And then I could solve for Phi2, okay? So when I do that, equation 4 plus equation 5 equals Phi2. I'm going to get Phi2 is equal to this. And I'm going quick because this is just algebra. And I mean, just take your time with it. Look through it, okay? So now that I have Phi2, I could use any of these two equations to find V2, right? So I used equation 5. That's what I put here. So I use that equation 5, and I found V2, okay? And don't look at this yet, okay? All this is, so I don't want to confuse you. There you go. Now that I found V2, and I have V2, so now I can use any of the three equations to find V3, right? In this case, I think I used this one, okay? I used equation 3, but actually, well, this is equation 3. It's just simplified. So I use this one, and I got my numbers, right? I solved for V3. So now I have Phi2, V2, and V3. And then I already have the Phi1, all the other ones, right? I mean, right here, they were 0. So that means I have this whole vector now. And And because of symmetry, we know that phi2 will be equal to negative phi4 because we have 5 nodes, okay? 1, 2, the middle of the beam, 4, 5. So that's 3. So I know this displacement is going to equal this displacement is going to equal that one. Phi is going to equal that one. These two phis are going to equal each other. Well, this one does too, right? But they're negative. In this case, 1 and 5 are 0, so it's negative 0 at this one. But whatever you get for phi2, you're going to get a negative phi4, okay? Now, hold on. These aren't even the answers. That's why they're clouded. The reason they're not the answers is because, remember, there's L over 6. But we're not going to do that. Just keep that in mind, okay? Just hold on. Do not do this yet. In this case, I'm just trying to show you the relation. V1, forces are equal to each other. So if this is a positive 2, let's say, this is going to be positive 2. If this is a negative 5, this one's a negative 5. It's symmetrical. And at 3, whatever the force is, right? In this case, V3 is equal. V3 will equal V3. V1 will equal V5. V2 will equal V4. Now, these are opposite in sign, okay? So this is phi1, this is negative phi1. If this is phi2, this is negative phi2, okay? Same magnitude as what I'm trying to say. In this case, I put negative phi4, same thing. And then phi3, this side of phi3 is going to equal this side of phi3. But our phi3 is 0. It's the same thing, okay? So that's the trick to that. Now, let's move on to the next step. I'll move this paper to the side. And I'll bring the next one. It's a long problem. Okay, let me see if you guys can see there. Let me hide this for now. All right, so now that you have your phis, this vector, right? That's what we just found, V2, phi2, and V3, and 0, 0, 0. So now we know this vector. This matrix stayed the same from this step, okay? I'm gonna show my paper again. It's just this matrix, okay? So this matrix was brought here. I filled out the displacement vector, and now I'm going to solve for my effective global nodal forces. Okay, that's what they call them. Effective global nodal forces. And these are the forces due to the element itself, okay? So I know all of this. I know all of this, so I can find all of these, right? 6 equations, 6 unknowns. But in this case, once you start doing the math, you don't even need to, like, do algebra. It's just do all of this, and that'll give you F1y. Do all of this one, and that'll give you M1, okay? And that's what I did here. So I don't want to show my whole paper, but like that, right? So F1ye is equal to EI over L cubed. Let me go ahead and use my other pencil again, right? We're on F1ye, so we're going to focus on the top row. That's 0, right? V1 and phi1 are 0, so you go to these 3. So you're going to have negative 1.5 V2 plus 1.5 L phi2, that's going to give you that, and then 0 V3. So you'll find F1ye, okay? Do the same thing for the other one. M1 is equal to EI over L cubed, negative 1.5 L phi2, L squared phi2, and then 0 V3. Do the same for all of them. These were, in this case, these were the only ones with two whatever these called, numbers, right? Because 0 V3, 0 V3. But the other ones, the remaining ones, they're going to have 3 numbers, okay? So once you do that math, take your time with it. Trust me, these are all correct. So you're going to have these numbers, okay? Now that you have your effective global nodal forces, now you use the nodal forces from step 6, which was this one, right? And you subtract these, and then that's going to give you your final reaction, okay? So it's like the element itself is fighting, but the reaction is also fighting. And it's going to, so if you saw a solution online, you're probably confused, which is probably why you're watching the video. And I was confused too. I was doing this at work, and it took me some time, but you'll see what happened and why it happened. I don't know why the book is wrong, but I can assure you that this is right, and I'm not sure what happened with the book. But now that we have this vector, now we're just going to use the equation, right? Your reactions are equal to the effective nodal forces. The effective nodal forces minus the nodal forces. So Whew, man, it's hot. So once you do that, you have your F1y, and this is what we're looking for. These are your reactions. These are the main ones now. These weren't the answers, okay? That's why they're clouded up. This is going to be the answer. So you're going to have 2WL, right? Effective nodal, right? 2WL. I made this into a vector. That's all that happened. Minus the nodal forces, right, of the system. The equivalent nodal force system, which was this vector right here. Minus WL, negative WL squared over 3, minus 3WL over 2, WL squared over 4, minus WL over 2, and then WL squared over 12. All right, so when you do that, you're going to get these numbers. It's just fractions, right? So find them, make the denominator the same number, and then just subtract them. So 2WL minus a negative number is going to give you 3WL. Do the same for all of them, okay? And this is where we plug in. These aren't the answers. You got to plug in L over 6, okay? So now that we have this, the answer set as a function of the substitution that we made earlier, right? These are here. Well, now we could get the final ones. And now we can also get the final displacements, okay? So that's what I did here. All right, cool. Let me move this one now. And now look at this one. Let me see, make sure you can see. There we go. All right. So all I did was just plug in L over 6 to these numbers. And that's how I got these, okay? Now, right here, you were technically going to get a number. But remember, this is a symmetrical system. So because we have a positive moment here, that means on the opposite side of the system, we have a negative of equal magnitude. And they should equal 0. That's the only trick to it. Now look. If this problem was modified, this is why the book is wrong. This problem was modified. This problem gave you a stiffness 2E. The answer would have been correct from the book if the whole beam was the same stiffness, okay? But because you made the beam stiffer, think of it logically. You guys are engineers, right? You guys got to start thinking. Think of it logically. If you made the beam stiffer, now the reactions don't have to fight as hard, okay? And I could prove this, and I did, because I was curious myself why it wasn't making sense from the book. I thought this problem was unsolvable. But no, I asked ChatGPT. I'm a believer of ChatGPT. I don't mind using it. Use it to your advantage when you can. But I don't ask it to do my work. I ask it like on things that I'm curious about. So I didn't ask it to solve the problem. I asked him, hey, if I had this beam, are the reactions smaller or larger? And it explains why. And I'll show you screenshots at the end of the video, okay? But I'll show you screenshots once I start showing the bending diagrams. But because the stiffness was increased, this changes your reaction magnitude. So normally, if this was all continuous beam, this reaction would have been WL squared over 12. And you can see that on Appendix D in the book, or you could see it from my previous video that I proved it through the bending moment equation, the differential equation, that this would have been WL squared over 12, WL squared over 12, minus WL over 2 minus WL over 2. But because we modified it, the bending moment changes. Now the reactions stay the same, okay? And ChatGPT will explain it if you ask it. But M1 gets modified. So look, this would have been WL squared over 12, but it became 13.17. That's a smaller number than WL squared over 12 than what theory would tell you. And that makes sense, right? Because the bending moment doesn't have to fight as much. Sure, it has to fight a little bit, just a little bit less. You would think it would be more significant, but no, in this case, that's what it is, 13.17. In this one, same thing. So it's like M1 is going clockwise, right? This is going to go this way, so it's a positive. This is a negative, right? Just sign switch, that's all. And then, my bad, this is counterclockwise. This is clockwise, negative, positive. And then the reactions, WL over 2, WL over 2, nothing going on in the middle, nothing going on in the middle, okay? So now, before I go to the bending diagrams, these are the displacements. All I did was I got these numbers, and I just plugged in L over 6, but these get to the third power, to the fourth power, to the fourth power. So it changes your results drastically, right? I just modified them in the way that I put the number up top, okay? So once you have all that, Now let's go to the bending diagram. That's the last part. Thank God, because it's just long. In this case, this is what the load looks like. WL squared over 13.17. Negative WL squared over 13.17. WL over 2 pushing up. Remember, it's not going down. That, when it was going down, it's because we were doing the equivalent nodal force system of the distributed load. These are now the reactions. Okay, so now they're going up. WL over 2, WL over 2, okay? To make the shear out of this, a clockwise or clockwise, counterclockwise moment isn't going to do anything to your shear diagram, okay? In this case, we start at WL over 2, push it up, boom, WL over 2, and then you go all the way down because it's a distributed load, right? It keeps increasing, right? It's adding so much weight per unit length, so that's what it's doing. And then WL over 2 pushes you back up. So cool. Now the area under the curve, right? So to get the bending moment diagram, a counterclockwise will push you down, remember, okay? So it's positive, like when you're doing these numbers, but on the bending diagram, it's gonna push you down, a counterclockwise moment. So this is all positive, and these are negative bending moments, positive, okay? Anything under 0, it's a positive bending moment. Anything over it is a clockwise moment, right? So, my bad, yeah, not positive. This is counterclockwise, clockwise, counterclockwise. So, let's do it the traditional way, right? We can still do it with variables. So what I did was look, for every unit length, which is the entire beam, you're gonna apply WL load, okay, right? Because your function is W times L. So if you're at L over 3, what's your shear gonna be? Well, just plug in L over 3 for that L, so you're gonna get WL over 6. You don't multiply them. You just plug in that L into this L. And that's why you end up at L over 3, right? At this L over 3 distance, you're gonna end up at WL over 6. Boom. And then it's symmetrical, so same thing, right? It's just the kind of just analyze one for now. Now, once you do that, you're able to find the area under the curve. The reason I did that is because it was a trapezoid, so I couldn't find that area. Now I have a triangle up top and a square at the bottom, or a rectangle. So take the area, WL over 2 minus WL over 6, that's this height. And that is WL over 3, okay? So WL over 3, base times height over 2, right? That's the area of a triangle. So WL over 3 times L over 3 is WL squared over 9. Divided by 2, because it's a triangle, right? You just want this half. You don't care about this half. You're going to get WL squared over 18. It's at the top region, so it's positive. WL squared over 18. Now do this one. Base times height, it's a rectangle. WL over 6 is your height. L over 3 is your base. Multiply them. WL squared over 18 is the area. So you have 2 WL squared over 18s. That's just WL squared over 9. Okay? So let's keep it going for now. This is all WL squared over 9. This here is another triangle. WL squared over 6 is your height. Base is L over 6, right? Because L over 3 is the entire length. But you just care about this half. So L over 6. So L over 6 times L over 6, or W. L over 6 times WL over 6 will give you WL squared. I'm sorry, WL over 6 times L over 6 is going to give you WL squared over 36. Since we're at the top, we're above 0, so that's a positive. And then same numbers, just negative now, right? WL squared over 36 negative, WL squared over 18 negative, L squared over 18 negative. Now we could do the bending diagram, okay? So the bending diagram, let me move this to the side, is right here. My bad, lost track for a second. But a counterclockwise will push you down. So we start at negative WL squared over 13.17, okay? We're gonna go up, and look, it's a big height. So that means your slope's gonna be high in your bending moment. That's what that means. Then as you go towards the center of the beam, well, let's just go up to here, right? You have a high slope, and then it gets a smaller slope. Then you get here. It's not 0, because this is 0, but you still have a smaller slope. And you went up a value of WL squared over 9. Remember these two together? So if you do negative WL squared over 13.17, plus WL squared over 9. Well, just get rid of the WL squared. Just do negative 1 over 13.17 plus 1 over 9. Well, you're going to get all the way up to here. WL squared over 28.42. Small one right there. Add the next one. So get this number, add 1 over 36, right? So 1 over 28.42 plus 1 over 36 will give you WL squared over 15.88. And that's your height, okay? And then it's symmetrical, so it just comes back down. Look, it was a high slope, right? So this is what I mean, high slope. That's a high slope. And then it starts decreasing. It's a low slope. There's zero slope, right? There is no slope. That's what that means. So it's just symmetrical, right? Just changes direction, but then it starts off a slow slope, low slope, low slope, low slope, and then high, 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 high. And then you have counterclockwise pushes you back up to 0. So that's your bending diagram, okay? And that's the answer. Now, if it was a perfect beam, remember, this was a modified beam with twice the stiffness. So it changed your results just a little bit. But if it was the same beam, if this beam was just a continuous, straight, same stiffness, and you could do it if you're really bored. Just do one whole beam, the same stiffness. I doubt you guys are going to want to do that, but you will get negative WL squared over 12 here, and you will get WL squared over 24 here, okay? So as you can see, this, decreased, right? Because imagine W's over here. W over 2's here, and then it gets bigger numbers, get smaller and smaller. So W over 12 is actually like right here, but it got smaller. Now it doesn't need to fight so much bending. This one got shorter, and ChatGPT will tell you that it got bigger, but you'll see, right? Just you'll see what I mean when I add the screenshots. But that is the answer. I don't want to make this video too long. It already took enough of my day today, but I'll show you guys the problems one more time, right? That is the top right here. This is the beginning. I hope I don't have to recover it, but I'm just going to show you guys just so you can see it one more time. That's the next page. I'm not sure right there. Okay. Then this page right here. Boom. Easy. And then this one right here. And that is the answer, guys. So good luck. We've entered the hard part of FEA. Hopefully it doesn't. I mean, it is going to get crazier, just FYI, but we'll see how it goes. All right. Till next time, guys.